Hi. So in this session, I want to talk about a very interesting algorithm to search something in an array. It's called binary search. I hope you know what binary search is. I'll give you a quick explanation of what binary search is, and then we'll try to write code for it. Okay. So given an array, or in case of Python, given a list, we want to binary search it. So first of all, binary search has a condition. List must be sorted. So in case you want to find something in your list, what you will have to do is, if you use linear search, you will have to pass through the complete list one by one. Binary search makes things faster, but it requires the list to be sorted. What is the concept behind it? So binary search basically says, in case of linear search, if I have 1000 elements, I need to look at 1000 elements to figure out if my element exists there or not. In the worst case, if my element is not present, then I need to go through everything to figure out if it is actually not there. Binary search says that you can take advantage of the fact that the array is sorted. Okay, so it says let's go to the middle. Let's say I'm looking for 10. Let's go to the middle. And if the middle character, or sorry, middle number is 15, then I know I don't have to look for 10 on this side. Because the array is sorted, there is no point looking for array on the right side because everything on the right will be bigger than 15. So you can only focus on this left part. Similarly, if I go to the middle and I find a 5, that means there is no point looking on the left side and you can just focus on the right side. Now, let's go back to the original assumption that it is 15. Now in this half-sized array, you can again go to the middle element and check what value is there. So this one is 15. Let's say you have 12 here. That again means there is no point looking in this part. You can go and focus on this part. Now let's say I go to the middle and I find a 5. That basically means 10 has to be somewhere in the middle and this part is gone again. So every time you check with an element, you are able to get rid of half the elements. And this half of elements is super fast. So for example, 1000 will reach 1 within 10 comparisons because after every comparison you're doing it half. So 500, 250, 125 and so on, within 10 steps you will reach 1. So you don't have to compare with 1000 elements, you just need to compare with 10 elements. It's amazing fast, right? It's super fast. So this is how we can use binary search. We could do it iteratively, but in this session we'll be doing it recursively. Okay, so how do we do it? So I have a list. I compare to the middle element. I need to find something, I need to search something. Let's say I need to search for x. So I go to the middle element, I compare it with x, and now I know whether I need to go to the left side or the right side. Right? I know whether to go to the left side or the right side. So in the previous lecture, we saw two options for this. If you want to go to the right side, let's say this is the area you want to go, this is negated. Then one option is that I can make a copy of it. But if you make a copy of it, that actually we end up losing all the benefit that we have with binary search. Because copying takes time, right? So I don't want to copy it. So I'm going to call the same function and I'm going to give it the start index. Okay, so what can happen the next time? You again go to the middle and let's say you figure out this area is useless and this is where you want to search. Now in your list, you don't only require start index, you also require the end index. Because you want to tell, hey, you can search only from this area to this area. Don't go here and there, only stay within this area, right? So binary search is an example where we have to pass the list, we have to pass the start index, we will also have to pass the end index, and this start and end will tell us what is the search area right now. So initially the search area is 0 to L minus 1, and slowly the search area will reduce. If the search area becomes empty, if there is nothing in the search area, that basically means that you could not find the element, and as long as there is something in the search area, you keep looking for your required element. Okay, so let's write code for this. Okay, binary search. We're going to get a list and we're going to get x that we want to look for. Let me name it A because I like L to be used for length. And we need to pass the start index and the end index. Okay, so initially the start index will be 0 and the end index will be length of A minus 1 because that's the search area. 0th index and the last index. This is the search area. Okay, what is my base case? I think my base case is when the list is empty. When is list empty? Can I say my list is empty? Can I say my list is empty if this is the case? I don't think so. Because in this case, there is one element left. You have start index and this is the end index. That means this is the only element that you need to search for. Any other example where basically what should be the base case then? I think our base case will be this. When start has crossed end, this is start, this is end. That means nothing left. If they are same, there is one thing left. If start is here, end is here, there is these many elements left. But if they have crossed, if start is here and end is here, that means we are done, right? So our base case will be if SI greater than EI, we can return, we didn't find it. We were supposed to return the index where we find it. I'm going to return -1. That we didn't find it, right? If you find it, you will return the index. If you don't find it, you will return -1. Okay, perfect. Okay, now what do we need to do? We need to find the midpoint. Mid is equals to SI plus EI by 2, right? SI plus EI by 2. If you do this, I hope you remember. If you do this, you get 3.5. That's not what you want. You want the index, the exact index, an integer. So we need to do integer division. But let's see. Let's say I have 6 elements from 0 to 5. What will be my middle number, right? 0, 1, 2, 3, 4, right? So you have 2 middle here. If you do 0 plus 5 integer division 2, you'll get this. So this will be your middle, which is fine. Both sides cannot be equal in this case. In the other case, let's say I have 5 elements. So 0 plus 4 integer division 2 will give you 2, which is perfect, which is your middle number, right? That's great. So I think we'll get the middle if we do this, right? We'll get the middle if we do this. Let me get rid of this. Now what you need to do is, if a of mid equal to x, you return mid. You have found x. That's what you were looking for. So you just return the index where you find x. Okay. The other option is a of mid is greater than x. What does this mean? Mid is bigger than x. That means you can only find on the left side. So you have some boundaries given to you. This is start index. This is end index. You looked at the middle, and a of mid is greater than x. That means x can only be between these limits, from Si to mid minus 1 actually. Mid is not equal to x, so you don't have to consider mid in the remaining work. Okay, so else if a mid greater than x, we are going to call binary search on a x. Start index stays same, end index becomes mid minus 1, right? And whatever output you get, that's what you need to return, because we are returning the actual index, right? So it will tell you if it says that it's at 7, it's actually in 7 in the complete array, not in this sub part. It's giving you the actual index. Okay, perfect. So you need to return this. Else, this basically means that you have this start index, you have this end index, mid is smaller than x, so x has to be somewhere here. That basically means we can call, so starting index becomes mid plus 1 and end index stays exactly the same. End index stays exactly the same. Okay, so I think this should work. Let's quickly call it on one array, right? The array has to be sorted. Don't complain that my function doesn't work if you take the input to be non-sorted, right? And I want to search for, let's say 3, and my start index will be 0, my end index will be, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements, so my end index will be 9. Okay, and it says index 1, which is absolutely correct, right? Let's ask it to find 2 for us, and it's returning minus 1, which is correct as well. Okay, so let's quickly try to dry run this and see how exactly is it working. So let's first take the example where we were able to find 3, right? So I'm assuming this is 1, 3, 5, 7, 9, 11, 13, 15, 16, 17, and I'm looking for 3. So initially this was my range, right? Start index is less than end index, so we don't hit the base case, we calculate the mid. So 0 and 9. Mid becomes 4, so we come to this number. So we compare with 9, we have 3. 3 is smaller than 9, so it does not hit this, and it goes, sorry, this is the one we did, 9 is greater than 3, right? So we will make a call on this. So that means the same list, the same number, but the end index is now here. So 0 and 3. We again find the mid, which becomes 1, and we end up coming here. In this case, mid is equal to x, so this function returns 1. So we return 1, the next one also returns 1, the next one also returns 1, and that's how we get our output. Okay, so now let me quickly dry run it for, let's say we try and find 19. Start index, end index. You go to the middle is smaller than 19, so your search area is this much. You again go to the middle, you go to 15. 15 is again smaller than 19, so your search area is only 16, 17. You go to the middle, which is 16. You again compare, and your search area is still on the right side, so it becomes only 17. So your start index is 17, your end index is 17. So you compare with 17, and it turns out that your middle is still smaller than 19, so you increase your start index to be mid plus 1, which basically takes start index here, end index is here, so start index has crossed end index, and that's how we know we need to stop, and we return minus 1. So that's how binary search is working. If you try and understand all of this, how exactly things are going to go in, and like how exactly the array is going to get smaller, how exactly your SI and EI will work, things will become complicated. So just focus on PMI, just think on the base case, just think of that the smaller problem is going to work fine, and things will be absolutely fine. Just make sure that you take care of induction step and the base case. Okay, thank you.